Awesome. First of all, I wanted to say thank you for those of you that came in to Liberty Time yesterday to go over some of the stuff for the retake. I feel like we had good conversations. We learned some physics, which is exactly what the point of this is. If you did not come in yesterday and you need to come in today, fantastic, I will be here. I need to write you a pass, so make sure that you get that before you go today or come visit me right before Liberty Time. If you need a pass, and we'll go over that. And just a reminder that we are going to retake those tests by Tuesday. If that doesn't work for you, you need to let me know. But most people have just told me already when they're ready to do it. I've got the retake ready and it's printed. So whenever you're ready, I'm ready for you. But you do need to do some reteaching before we do that. So again, if you have questions about that, let me know. Otherwise, we're going to move on to this unit. We're going to do a little warm-up graphing task. Then we're going to talk about projectile motion. That's going to be our whole day today. We got practice problems, and you do have homework for tomorrow. So if you don't have that written down yet, you may want to just write that down now. This is up on Canvas as well, but, you know, they have to look at Canvas, and that takes another step, maybe. I don't know. I mean, it's really not that hard. That's where I got it from, page 98, 1, 2, and 3. This is going to be a problem-solving kind of day today. So we're going to start at the beginning. So here is a situation, a picture, a thing to look at. I'm going to zoom this in just a little bit so you can get a sense of what's going on and read it a little bit better. And I'll read it to you just in case it's hard to see. But we've experienced this already. A rock is dropped from the top of a cliff at the same instant that a rock B, or rock B, is thrown horizontally from the cliff. Do you feel as though we've talked about this situation before? Perhaps even that you've seen it before your very eyes? I hope. We had the ball bearings, right, last Wednesday, a week ago today. The rocks are identical. A student draws the following graphs to describe the motion of the rocks using a coordinate system in which the positive vertical direction is up and the positive horizontal direction is away from the cliff. The origin of the coordinate system is the point where the rocks were released from. So just to be very clear, what they mean by that is that if you were going to draw the axis, it would look like this. So this is the horizontal direction, and this is the vertical. That should be pretty clear, but just in case you're confused, okay? So I'm going to zoom this out a little bit so that you can see these graphs. This is kind of like the question that was at the bottom of the test that you took. Here's a graph. Did they do it right? Okay. I love this because then I can tell if you really understand it or not, right? Because you have to think through what they did. So I'm going to give you a couple minutes to look at this. You may want to just draw like a sketch of this picture so that you remember, and then draw these 4 graphs. So this is rock A, horizontal and vertical. This is rock B, horizontal and vertical. Again, horizontal is the x-axis, vertical is the y-axis in terms of that. So take a couple minutes to look at that. If they're right, tell me that they're right. If they're not, explain to me why they're not so that we can have a conversation. So we can kind of talk together here. So let's see where we're at. I feel like hopefully we understand the question at least. Let's kind of make sure that we're doing okay here. So rock A, let's talk about rock A. Tell me about the motion of rock A. What is rock A doing? It's going straight down, right? It's the frog that's just falling. Okay? It's the frog that's just falling. So is there any velocity horizontal? Is there any velocity for that frog in the X direction? Watch it. Let's watch it again. Here it comes. Is there any horizontal velocity for that frog during the whole story?
Don't believe so.
Don't believe so. So I think that this one is probably incorrect. And how can I fix it? What would be the correct drawing for that graph? Absolutely, a line on the x-axis. Just like that. Okay? So we're going to fix that one. We're going to get rid of that. That is wrong. How about in the vertical direction? Watch the frog again. You feel like you've watched frogs fall a lot this year already? And it's just going to keep happening. So let's watch the frog fall. Tell me about its velocity right when I let go. What is it? Initial velocity is 0, right? And then what happens to his velocity as he falls? It increases in the negative direction. So what's that graph going to look like? Is it going to look like this?
No. It's going to start at the x-axis.
It's going to start at the x-axis, and then what's it going to do? It's going to go down. Does that make sense? Absolutely. Nice job. So it's going to start at the x-axis, and it's going to go down in a straight line, constant velocity. What does the velocity of this represent, ladies and gentlemen? Or not the velocity, so that's not what I would ask. You're like, well, I don't know. What does the slope of this graph mean? What is the slope of the velocity versus time graph? Yeah, it is getting faster in the negative direction. Tell me about the slope. The slope of a velocity versus time graph. The slope of a velocity versus time graph. Change in y over change in x. Change in velocity over time. The slope of a velocity versus time graph is change in velocity over time. What is that? That is the acceleration. That is the acceleration. Okay? Is the frog accelerating in the vertical direction? Watch him. Is he accelerating in the vertical direction? That means, is he changing speed in the vertical direction? He is. He's getting faster and faster and faster, isn't he? Because it's negative 9.8. So what should the slope of this line be? This is the acceleration due to gravity. If you have not yet written this down in your notes somewhere where we're going to start our day, I would love for you to do this. I would draw this picture. This one right here. Okay? Draw that picture. And for rock A, go ahead and draw the correct velocity versus time graph for the horizontal. So this is the x direction, the velocity in the x direction. And this one down here is the velocity in the y direction. Again, this is the wrong answer. Okay. This graphing business is not going away because it's so important. So there is no acceleration in the x direction. It's not speeding up or slowing down. Is there acceleration in the y direction? Yeah, for sure there is. And we know the value of it even, don't we? 9.8 downward. 9.8 downward. How do we do with rock A? This one we should have been able to do like a week ago. This is just one-dimensional motion, okay? So rock A is the one that's just falling straight down, just like you did with the balls when you were out at the balcony, right? We timed it, we watched it, it all happened. The horizontal velocity, we didn't even think to ask about it because it was all in one direction. The vertical velocity starts at 0 and it goes down, 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 down. Okay? Speeds up as it's going. So far, so good? Okay. Knowing what you know about rock A, do you want a couple minutes to talk about rock B? Yeah? I'm going to give you a couple minutes to talk about rock B now. So on your whiteboard, if you want to erase these or fix the rock A stuff, that's absolutely fine. I want you to talk through rock B, and then we'll go through it. Okay? Here we go. Okay, so What did you say about rock B horizontally? Let's think about rock B horizontally. Is rock B moving in the horizontal or the X direction?
Yes.
Absolutely it is, yeah. So that's exciting, yay. Is rock B, this is after it's been thrown or kicked or launched or whatever, no matter how it's happening, it's after it's left the contact of that thing. Is rock B, and assuming that we're in a vacuum so there's no air resistance, speeding up, slowing down, or staying the same speed? Staying the same speed. Because it's not touching the hand that's throwing it or the foot that's kicking it or the rocket launcher that is launching it, right? There's no air to slow it down. So there's no reason it's going to speed up or slow down. It's going to go in the same speed the whole time in the X direction. So how do I graph that on this? Is this right?
No.
No, what should it look like?
Bring it up.
Bring it up a little bit? Yeah. Yeah. So it's going to be something like that. Is that okay? Yeah. This is so exciting. Tell me about this one. Is this one okay? It doesn't make any sense. I love that. Why? I don't know. Okay, let's think about it. The vertical direction. So we have to think about this frog or this ball or this whatever, the rock. As it's going horizontally, it's also doing what? Falling down. The motion of the rock falling down, rock B, because it's going over and down and over and down and over and down, right? You can think about it kind of like that. Is rock B accelerating in the downward direction?
Yes.
Jordan says yes. Like some of you are like, you said that like you meant it. Can you tell me why you're saying that with such conviction?
Because everything being accelerated down.
Unless there's something like pulling it or pushing it, right? Yeah. So I drop it, right? If I throw it, right? Regardless, it's being pulled down, which means that it's traveling. Whoa, you got an arm. Good job. Love it. It's being pulled down with an acceleration of how much? -9.8. So what should the graph look like? Yeah. With a constant slope, right? What should that slope be? Boom. So is this graph okay? Yes, it is. It's the only one. 1 out of 4, 25% for this kid. Hopefully now if you had a question like this on a test, you could do it.
So they aren't just the
They are not. No. You're trying to like overthink the people that are writing these questions, aren't you?
Yeah.
Yeah, Jordan's like, I got this. Oh yeah. Yeah, they're kind of, I wouldn't say tricksy, but they definitely pay attention to what they're doing. So let's look at this. I'm going to draw this again, kind of like you have it in your notes, just because this is kind of convoluted and weird. I'm going to draw this over here again. So I'm going to say the velocity in the X direction and the velocity in the Y direction. This is for rock A. And then for rock B, we're going to do the same thing. I just want to make sure that this really makes sense, because you guys, if this makes sense to you, then the projectile motion stuff is going to be really easy. If this doesn't make sense to you, then I want to get it fixed now. Does that make sense? Because once we get this, I think it's going to be a good story. So this is going to be Vx, and this is going to be Vy. These are all T. So again, if you don't have this all written down already, you're going to write it down now with me. The velocity in the X direction, this is for rock A, the one that just goes straight down. That one was just a horizontal line on the 0, right? Okay, because it didn't have any velocity at all in the X direction the whole time. It was always 0. The velocity in the Y direction started off at what? 0, and it fell down, 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 and as it did it, it sped up, right? Negative velocity, negative acceleration. It gets faster and faster in the negative direction. So we're going to draw a line, a line at an angle. We're going to remind ourselves that the slope equals negative 9.8 meters per second squared, and it is accelerating down, right? It's falling and it's accelerating. Rock B, that was the one that was being launched. its velocity in the x direction doesn't change? Does the velocity in the x direction change for rock B? Velocity in the x direction.
Yes.
Velocity in the x direction?
Oh, sorry, it's constant.
It's constant, right?
Yeah.
It stays constant. I just want to make sure this is actually sitting in your heads and you're not just, agreeing with me. That's the important thing. Because agreeing with me is fine until you sit down and take a quiz. And if you don't really understand it, then you're going to be a sad kid. So there we go and then this one, what is this one going to look like? Same as what?
We need the negative 9.8 slope.
Same as the one that's falling, right?
Yes.
Okay. So the important thing to notice here, friends, is that the velocity in the y direction graphs are exactly the same. Okay? The thing to notice and the thing to pay attention is that a motion in the x direction does not affect the motion in the y direction. They are completely independent from one another. They are completely independent from one another. Okay? It's weird. It's weird.
Throw a million miles an hour going in that, throwing it downward.
Mhm.
You just drop the ball. And
Yep. Yep. Yeah. Oh, yeah. They've done, like Mythbusters. I don't know if you guys know Mythbusters still, but they've done this, right? With like a bullet from a gun and dropping a bullet. Same time. Same time. It's weird. Yeah.
So they feel like air pushing it up because if you throw a frisbee, it's going to fly.
Right, so frisbees are weird. There are a couple of things going on. So frisbees, number one, you have to take into account air, right? So that's for darn sure. And the other thing about a frisbee is you're not just pushing a frisbee, you're giving it some rotational acceleration or rotational motion as well. And that rotation also affects its trajectory. It's weird. Because then you can get different kinds of spin on it, right? If you throw a backhand, then it's going to be different than if you throw a forehand, all that kind of stuff. Like, so there's a lot of physics in frisbee throwing. Yeah.
We don't have to learn about
It may be a coincidence. It may not be that the physics department frisbee team at my college was one of the best IM teams at our college. Just saying. I don't know. I was not on it. I just cheered for them. But anyway. Yes, we will learn about some of that, but not right now. Yeah, this is a little bit, we're doing kind of the simple stuff to start. How are we doing? Are we okay? So far, so good? Okay. I feel like I wanted to say one more thing about it, but I don't know what it was. So we're going to just try out some problems with this now that we have a sense of kind of what is going on. Okay? So the first one that we're going to do is from your book, I think. Yes. So you might want to just write this down. We're just going to look at this problem together. I'm going to go through this with you. I think I may have said this to you last week, but I'll say it to you again. In my experience teaching projectile motion, students are of one of two situations. Either they're go it alone people. You do not have to copy this whole problem down. It's on page 98 in your book, so please don't copy it down. Okay? So either they're go it alone people, like, I just got this, head in the sand is going to go. And I will be honest, many of them get stuck. And then they get frustrated, and then they are like, or they give up, one of the two. The other people use my patented plan for solving projectile motion problems, and usually they're like, I got this, I can do it, no problem, okay? I feel like I'm on that infomercial, and I don't mean it that way. I'm just letting you know that I've been teaching this for a long time, and this is one of those things that works. So, I won't even say, it doesn't even cost like 4 easy installments of $9.99. Like, I'll give it to you for free. Yeah. I'm going to teach you how to do it right now. I'm recording it so you can watch it as many times. Like, if that's what you need to fall asleep. No, hopefully it's not to fall asleep. Because you can't sleep and you're like, I just need to watch some physics. You can watch this over and over. So you're going to write down on your paper if you want to, that this is page 98, sample problem D, so you can look at it again and again and again. The problem is written there. I would not follow the solution that they have in the book because they do it in kind of a weird, convoluted way. Follow the Carbling approach. It will make you happy. Okay? So here we go. We're going to take a look at the situation here first. Has anybody been to Colorado? Cross the Arkansas River on the Royal Gorge Bridge, anybody? There was one year I was teaching this and I had a student who was like, I've been there. I was so excited. I was like, I've never been there, but it sounds fun. It's a really high bridge, 321 meters above the Arkansas River. Suppose you're standing on that bridge and there's a rock sitting there and you just kick it, okay? You're going to give it a kick, horizontal kick. It's going to go off the side of the bridge and down and splash into the river below, okay? The question says it's 320 meters above the river. It's got a horizontal displacement of 45 meters, so it goes 45 meters. And then, yeah, we're going to draw the picture. Yeah, exactly. And then we're going to find the speed. So first thing that I want you to do that I would do on all of these problems is to draw yourself a little picture. So I'm going to draw a picture. Here's the bridge. And here's the water below. And we're going to go ahead and write down some things. So this distance here is how much? How high was that bridge? What does it say?
321 meters.
321 meters. Okay? The rock is going to fly off of that bridge. So here's the rock at the beginning. It's going to fly off of that bridge. It's going to experience some... That's awesome. I don't know who's making that noise, but it's fabulous. Thank you for that. Not drawn to scale. It's going to travel a distance in the x direction of how much?
45 meters.
45 meters before splashing into the river. Okay? I would strongly encourage you to draw an arrow to show its initial velocity, just so you know where it's going. Okay? At the beginning. For the problems we do today, that's going to be pretty simple every time. But in a couple of days, you'll be glad that you've gotten the habit of drawing those arrows. Okay? And we want to know that initial velocity. That was the question. So I'm going to write VI equals question mark. How are we doing so far? Got a picture drawn. Good for us. Now we're going to write givens because that's really the beginning of the problem, right? We're going to write our givens down. So this is the game, friends. We're going to write givens, but instead of just writing them kind of willy-nilly, we're going to write them on a little chart to keep everything organized. Because 99% of all projectile motion problems have 7 things that you'll need to know. So we're going to just write them down in the same order every single time. So here it comes. Are you ready? Yeah, Ms. Garbling, that sounds great. Displacement in the x, initial velocity in the x, acceleration in the x. I'm going to leave a space. I would encourage you to set up this chart just like I'm doing. Displacement in the y, initial velocity in the y, acceleration in the y, and the thing that ties it all together is time. Okay? So I've got 1, 2, 3, 4, 5, 6, 7 things. Some of which I know, some of which I don't. So after I draw a picture, I'm going to set up my givens chart, and then I'm going to fill in anything I can fill in. So, what can you tell me? There are a few of those things. Take a look at the picture, take a look at the problem. Raise your hand if you can tell me one of the things that goes in one of those 7 spots. Go, Mira. Look at her doing 2 in 1. She's like, I got this. Displacement in the x is 45. Yes, it is. Displacement in the y, I almost agree with you. I almost agree with you. You said it was going to be 321 meters, right? But Shahad's going to say what? Negative, she says, because it's going which way? Down. And I want to make sure that I pay attention to that. So it's going to be a negative 321 meters. Excellent. 2 down. There are 4 left or 5 left that we can fill in. I believe that we can fill in 1, 2, 3 of them. Isaac's got 1. What you got?
Acceleration in the y direction.
It's what?
Negative 9.8 meters per second.
Indeed it is. All right, 2 more. I think that there are 2 more that we can fill in. They're both really nice things to fill in with. Gosha, how much you got?
VI and Y 0?
It is. Yes. VI in the y direction is 0, because if you look at the pink arrow here, the pink arrow is only in the x direction right now. Do you see that? So that is awesome. That makes our life a lot better in this case. We can say that VI in the y direction is 0 meters per second. Excellent. What else have you got?
Two graphs that we just did, the bottom ones we said are always going to be negative 9.8 meters per second.
That's true. The acceleration in the y direction. Yes. Yeah. So let's look back. Are you talking about this chart here? So let's take a look. Remember that we said that the slope of this line tells us the acceleration, right? What's the slope of this line? What's the slope of it? Rise over run. 0? If the slope of this line is 0, that means that the acceleration in the x direction has to be what? Say it, Aurelia, you got it. You're so excited. 0! Yes, zeros make our life better. We want things to be 0 if they can be. So we got an acceleration in the x direction of 0 as well. Oops, that's not what I wanted. Was it this one? There we go. Sorry about that. AX is 0. Fantastic. This is what we want to know, right? The initial velocity in the x direction, that's what we want to know. So I'm going to put a question mark by that one. And do we know the time? Yeah, but at this point, we don't know it. Would you agree?
Yeah.
We don't know the final velocity in the y direction either. Sometimes people ask you to find that, but I'm not going to do that today. I'm thinking, though, that if we have this stuff, we've got an acceleration, an initial velocity, a displacement, I need a time in order to figure out this. Do you see what I'm saying? If you look at the equations, on your equation sheet, pull that equation sheet out if you don't have it yet, and you can come grab one if you need one. I want you to look at this equation sheet. And Josie, did you get our t-shirts made yet? You didn't get our t-shirts made yet? She's like, not yet. Take a look at those equations. Again, we're just looking in the top left-hand corner. That first equation is only for if it's not accelerating. In the x direction, is it accelerating? It's not. But in order to use that, we would need v, x, and t. And we have 2 of those that we don't know. If you have 2 unknowns in an equation, can you solve it? You can't. If you look at any of those other equations, in order to find the velocity, you would need time. You have to have one or the other. So we're kind of stuck. So that means we can either walk away and say, I guess I can't do the problem. That's not the right choice. Or we can say, oh, but wait, we know a bunch of stuff about the y direction. We know the displacement, the initial velocity, and the acceleration. And I know an equation that has those 3 things and time in it. So I can solve for time. Are you with me there? Okay. 99% of the times when you solve a projectile motion problem, you're going to use the y stuff to solve for x, or the x stuff to solve for y. And the thing that ties it all together is the time, because the time is the same. All right, so we're going to keep cruising here. Here we go. We're going to set this up as 2 little separate problems. So I'm going to do the y stuff first. I'm going to label it y stuff just because then you can kind of keep in mind what's happening here. Okay, but after I've written down the givens, I'm going to look for an equation, my favorite one, that has all of these things. D, V, I, A, and T. Can you find it, Josie? Can you find it, Mira? It's the one we love, right? I'm turning into a subscript lover. I think they're great. Subscripts, these little Y's here are great because they let me know what I need to put in. So I'm doing all of the Y stuff, and I'm going to put Y's here so I don't forget that I'm only looking up here at the things labeled Y. Now, before I get overwhelmed and scared because I've got a T and a T squared, I'm going to look and see if I can be clever. Is there anything in my list that is 0? Yeah! So let's get rid of that stuff first. Where is there a 0 in this big, long, scary equation? The VIY. And 0 times anything is 0. Woohoo! So we're going to get rid of that one. See you later. So now I know you guys are enthusiastic about that just like me. dy equals 1/2 ay t squared. You've solved this problem probably about 12 times already in your life. Okay? Maybe more than that. Maybe 30 times. I've probably done it hundreds or thousands of times. I know you can do it. Let's get t all by itself. How are you going to get t all by itself? Divide by what? Let's divide by 1/2 ay. Let's do it. Bless you. And then I need to get rid of my t. I need to get rid of the squared. How do I undo a squared? Square root, right? We're going to take the square root of both sides. And I'm going to rewrite that in nice form. It's the square root of dy over 1/2 ay is equal to t. That was negative, what was the number? 321 divided by 1/2 times negative 9.8. You can plug that in and you can then tell me how long it takes for that rock to hit the water. If you haven't plugged that in yet, I want you to plug it in. I want you to have a calculator out in front of you, and I want you to do it. Do you need some calculators? I can come around like, look over right, maybe I'll calculators. I'm going to skip through the forest and hand out calculators. Do you need calculators? Don't say, do you need calculators? All right. My friends over there, do you guys have calculators? Josie, do you need one? Okay. Everybody's going to do the calculation so that everybody feels good about it. So that you don't have to rely on me to do it for you. Yes, ma'am. Yep.
Okay, I'm good.
Yep. Awesome. That's okay. Ask that question every time. Because the more you ask the questions, the better you're going to feel about it. I'm so excited about this, you guys. This is like, woo! Did you get a value? How long does it take that little rock to fall? Check with your table mate, make sure they agree. I got this. Yay, look at us, we're so cool. Or, I didn't get that. You can do it in lots of steps. You can do it in one step. I would recommend if you do it in just one, that you use a lot of parentheses. Parentheses are your friend. For sure. What do we get?
I don't know, I got
8.09? Is that what you were going to say too?
Yeah, I mean, I rounded it.
You rounded 8.1? I'm cool with that. Either way is fine. Do we have other people that agree with that?
Yeah.
Yay, nice job. All right. Are we done with the problem?
No.
But we're almost there. The Y stuff is always harder than the X stuff. So let's just do the X now. It'll be no problemo. Look, now we've got T. So we can put T in here. It's 8.09 or 8.1. Either way is okay because you're going to show me your work when you do this. And so I'll be able to tell what's going on. Okay? So you've got a time of 8.9, 8.09 or 8.1. Now we're going to look at the X stuff. So I'm going to write the X stuff next. Here it comes. X stuff. We're rocking this out. We got just a couple minutes here. So guess what, friends? Same givens. That means it's going to be the same equation. Rocking those t-shirts. Here we go. It's going to be dx equals vxt plus 1/2 ax t squared. Anything in this one go to 0? Let's be clever. Let's make our life easy. The ax is 0, right? Life is good. 0 times a whole bunch of stuff is still what? 0. It's gone. Catch you later. See you another day. Not right now. And so now we've got dx is just vxt. I can do that. You can too. In fact, you've done it many times. Like on a test, on a quiz, on some homework. It's all been there. So dx equals vxt. That's the initial velocity, by the way. I always forget to write my little vi. Solve that for v. So you've got vix is equal to dx over t. Hey, I've seen that one before too. Now we just got to put numbers in, right? No problem. You got this. Dx is 45. So I've got initial velocity in the x direction is going to be 45 meters in 8.09 or 8.1 seconds. What have you got? Did you plug it in? Go, Ben.
I got 5.5 speed.
5.5, what'd you say?
Repeating.
Okay, so we'll call it 5.6. What are the units here? Look at you guys. We just did it. We got a whole projectile motion problem done. That's a lot of stuff. But it's not that bad if you just take it one step at a time. So you got 3 problems kind of like this for homework tonight. I want you to rock through them. I want you to do your best. We'll start with those tomorrow. We'll get as far as we can. You can leave the whiteboards on your tables. Have a fabulous day. I will see you tomorrow or today if you're going to come in and get some help for reteaching.